Okay, now this is 2.5, the graphical and analytical approach to cruising performance analysis. Now let's combine the thrust, okay, the thrust available and the thrust required curve, and also the power available and the power required curve. Let's combine and do analysis from here. Okay, if you are wondering in your textbook, okay, this lecture is related to a subchapter 6.3 until 6.6. Okay, now this is if you look at this slide, there are four graphs, okay, four plots, four graphs. But the main graph will be this one, the thrust versus velocity, and the three graph, okay, the three graph at the side and below the T versus V graph is the supporting, okay, to help me explain to you what happened. Okay, all right. Now this is this thrust versus velocity, or this is airspeed, okay, graph plot is for a jet powered aircraft, and assuming it is idealized or simplified turbojet or turbofan. And this graph, okay, this curve is a thrust required, okay, basically it is the drag of the aircraft, and this straight line is a thrust available, okay, which is basically the amount of force, okay, produced by the engine, okay, the turbojet or turbofan engine. And this is for one specific altitude. One specific altitude. I repeat again, only one specific altitude. Okay. So I have not yet discussed about the effect of altitude. This is assuming that it only happened at one specific altitude. For example, at sea level. Okay. Now, and if you look at this, a thrust required, okay, if we or drag, it has this kind of curve, meaning that the required amount of thrust for you to stay at steady, to fly steady and level at constant airspeed is this. For example, you need this much amount of thrust if you were to fly at this airspeed. Or what is the lowest? Okay, for example, this the blue point is the lowest drag. Okay, this it is the lowest amount of thrust needed for you to fly at this velocity. Or okay, or this in this case the velocity at L over D max. Okay, or velocity for minimum drag, you have to fly at this. Okay, and there are other points. Okay, so let me explain to you. Okay, so the blue point, okay, the blue dot here is the velocity at minimum drag. So if you want to fly at the minimum thrust required, so fly here. So for jet aircraft, if you fly at this condition, at this airspeed, you have the lowest drag, hence you can reduce the amount of thrust available. Okay, you can reduce the thrust to this level. Okay, you can reduce the thrust, and maybe you can fly a very long time. Okay, you can fly a very long time. But there are also for jet engine. If you were to fly further, okay, far, you may not need to fly at minimum drag. You fly at velocity where your CL to the power of half over CD is maximum. So you need to fly here a little bit faster, then you can go far. Okay, you can go far. Okay, and then you are wondering, what is the maximum? velocity or maximum airspeed of my airplane. And maximum airspeed of my airplane is determined by the maximum thrust available that I have. Okay? This this thrust available line actually represents the maximum thrust available from the jet engine. Okay? So if you fly within this region where your thrust required is lower than the thrust available, okay, then actually you have an excess thrust, meaning that you can fly within this region. But if you try to fly outside of this region, your thrust required is more than thrust available, and your airplane cannot fly that fast. Okay, so this green, the purple dot here is the point where your thrust required is equal to the maximum thrust available, and this determines your maximum airspeed or Vmax. Okay, so this is your Vmax. You cannot fly here because your airplane cannot produce enough thrust to counter the drag. Alright, so you have minimum drag airspeed, you have airspeed at maximum CL to the power of half over CD, you have maximum airspeed, and you have minimum airspeed. So if you look at this, there are 2 points where the drag and thrust available intersect. So this one determines the maximum airspeed, and this one determines the minimum airspeed. Okay, so in this case, if you fly slower than minimum drag speed, okay, the thrust required or the drag increases. Okay, as you go slower and slower, it increases up to a point where it will intersect the thrust available. So this is the minimum speed that is possible, okay, based on the maximum thrust available. Okay, minimum speed. However, you have to look at the aerodynamics of your plane. Okay, so if it happened that okay, your stall speed is higher than minimum speed, then your minimum speed is determined by any of these two which is higher, because you cannot fly lower than stall speed. Okay, so then in this case, since the stall speed is higher than minimum speed, the minimum speed is actually the stall speed. Okay, the stall speed, because this is a limitation of your wing. Okay, so I've also plot here the CL versus angle of attack. In this case, the angle of attack is positive to the left. Okay, so as you go at high speed, for example, you fly at low angle of attack, and as you reduce the airspeed, the CL will increase. Okay, CL increase until you find an optimum CL at minimum drag. Okay, and until you stall. So this right is the maximum CL at alpha max or alpha stall. Okay, so this is your stall speed. Okay, there is another term. Okay, there is another term, a yellow one, but not so relevant for jet-powered aircraft. Okay, that is the airspeed at CL to the power of 1.5 over CD max. Okay, this is more relevant for propeller, and this is the airspeed where your power required is minimum. Okay, the airspeed where your power required is minimum. But for jet aircraft, it's not that relevant. The most relevant is velocity or airspeed, to find the airspeed at minimum drag and the airspeed at minimum CL to the power of half over CD max. Okay, so few points. Okay, so if you look on the left, okay, the CD versus CL plot. Okay, the CD versus CL plot. You can see that of course at this store speed, your CL is maximum. Okay, the maximum CL, and your CD is the highest. Okay, and as you go faster, you will reduce your CL. Okay, reduce your CL. Your CD will also reduce until you reach the blue point where your CD is minimum. Okay, minimum CD. But minimum CD is not the lowest CD in terms of aerodynamic. In terms of performance, is called minimum CD. Okay, because it happens at the maximum lift to drag ratio or CL over CD max. Okay, if you look at this plot is the aerodynamic efficiency over CL. Okay, it happens at maximum CL over CD max. And for jet aircraft to cruise, okay, to cruise farther, okay, you need to fly at maximum CL to power of half over CD max, and it happens at CD squared minimum. Okay, minimum CD squared. Okay, this one. Okay, and this is CD naught. Okay, CD at zero lift. Okay, so there is no lift here. It happens at CD minimum. So these are some of the points you need to identify during the cruising. Okay, and from here we can see, okay, from this first part of lecture you can see what is the maximum airspeed attainable for the aircraft, what are some of the optimal airspeed. Okay, in this case for jet aircraft, the blue is for uh, the longest endurance, for example, and the green one for the longest range, and then the stall, okay, the stall speed and the minimum speed. Okay, that's all for the first part.